Okay, so now let me tell you about a second application of these bipartite expander graphs that we've been talking about. And this one will really use heavily the fact that we have explicit, deterministic, and even fully explicit constructions of expander graphs, because the topic is derandomization. Okay, so this is application 2, derandomization. So we talked about derandomization some already in this course. And what I'm going to show you now is how it's almost like a little magic trick you can do if you're not interested in fully derandomizing an algorithm, but simply getting better probabilistic guarantees about your algorithm without using more random bits than you need to. And as I said, it's a bit like a magic trick. You'll see that we get something for nothing almost from these expander graphs. So to set this up, let's set the stage for a very simple randomized algorithms derandomization problem. So let's say that A is a randomized algorithm with one-sided error. So like an RP style algorithm, error, for a decision problem P. And normally I don't like to use the letter P for a decision problem because it reminds one of complexity class polynomial time. But let me stick with it, P. And one reason I chose the letter P is an excellent example is the decision problem primality. So imagine this randomized algorithm A is trying to decide if a given number is prime or not. And the Miller-Rabin algorithm, the most standard primality testing algorithm, is a randomized algorithm with one-sided error. It has the property that, well, before we get to the property, let's imagine this viewpoint of a randomized algorithm. One way a viewpoint of a randomized algorithm A is, it gets in the true input X, and, it outputs yes or no. And it flips some coins as it's doing that, and it gives the correct answer with high probability. But it's also nice to think of this viewpoint where A is a deterministic algorithm that gets access to random bits. And that's how we'll think about it again. So let's imagine that A is a deterministic algorithm that gets access to R, a random n-bit string. Okay, so we kind of pull the random bits out of the algorithm, and now, to say that A, solves the decision problem P with one-sided error, and we'll assume it has error 1% for this example, we'll assume that has these properties. So if X is a yes answer, if X is in the language, think of primes again, then when you choose the random string R uniformly at random, the probability that you get the yes answer out of A when it's fed X and R is 1. Okay, so if X is in the language, it'll always say yes, and if X is not in the language, then the probability over R that you get the wrong answer, yes, is at most, as I said, 1% or 0.01. Okay, and this is kind of like how the Miller-Rabin algorithm behaves. If you give it a prime, it will always say prime, and if you give it a composite number, it might possibly rarely accidentally say prime, even though it's composite. Okay, so what we want to imagine for this sort of little derandomization magic trick is that we want to reduce this error without using any more random bits. Or without, let's say, conserving random bits. Okay, so we'll imagine that random bits, like randomness is super precious. And so we really want to use very few random bits, but we want to decrease the error. So let's also say that A is an algorithm that takes time t. So one thing you can do to reduce error is the thing that you always do to reduce error. Just repeat the algorithm a bunch of times, and in this case, say yes if and only if all the answers were yes. Okay, so that's the standard thing to do. You could repeat, let's say, d times the algorithm independently with fresh random independent bits each case. And what would happen? So you would use d times t time, and you would use d times n random bits. Okay, we're assuming that each run requires n random bits. And what is the error probability of this repeated algorithm? Well, it's 1% to the power of d. Okay, and that's the classic standard error amplification or error reduction thing. If you pick d to be, 100, that's pretty good. You take 100 times more time, and your error probability goes way down. But you have to use 100 times as many random bits. And, in this little example, I want to really focus heavily on conserving random bits. So I'll consider that quite expensive. So here's the second strategy that uses fully explicit expander graphs. And what we're going to do is take one of these bipartite expanders of the type we've been talking about, this bipart expander, but on 2n plus 2n vertices. Okay, so I'll explain what I mean by that just now. But what I'm saying is, well, actually, these bipartite graphs we talked about before had n on one side and 3/4 n on the other side. Just ignore that 3/4 thing. Let's assume they have the same number of vertices on the left and right. But let's assume that same number of vertices is 2 to the n. Now, this is I'll put an exclamation mark here because this is a bold move. What we're relying on here is this strongly explicit property. Okay, so let me remind you, what does that mean? We're assuming these bipartite expanders are strongly explicit. So we don't literally write down the adjacency matrix of this bipartite graph, vertex set L and R with 2 to the n vertices here and 2 to the n vertices here. But the algorithm sort of mentally knows about it. And what does it mean that it mentally knows about it, this strongly explicit thing? It means the algorithm in polynomial time can understand the adjacency relationship of this graph. So if you're the algorithm and you think of the name of a vertex over here, okay, this is named by n-bit strings. And you also, we'll stick with the D regular graph or the 64 regular graph. If the algorithm thinks of a number between 1 and D, or 1 and 64 specifically, then it can figure out in polynomial and n time the names of these D neighbors. Okay, these are also n-bit strings. And the point is that you can work out the neighborhood or neighbor relationship in poly n time. Okay, so this randomness reduction, this error reduction algorithm that conserves randomness is going to sort of take this graph on 2 to the n plus 2 to the n vertices. And remember, once again, what is the property of this, the expansion property of this graph? It's that the neighborhood set of any subset S, okay, so if S is a subset of L, and the size of S is at most, 0.02 over D or over 64 times n, then the number of neighbors of S is at least 0.8 times D times cardinality of S. Okay, so what is the actual algorithm here for trying to decrease the error in algorithm A? So step 1, pick a vertex L on the left-hand side uniformly at random. Okay, and that's picking a random n-bit string, so this definitely costs you n random bits. No doubt about that. But now, just consider its neighbors. Let R1 through RD be L's neighbors. Okay, so these are right-hand side vertices, which are also named by n-bit strings. And by the strongly explicit aspect of these bipartite graphs, where you can compute this neighborhood relationship in polylog the number of vertices time, or poly little n time, this calculation of computing these vertices takes poly n time, which is nice. And now we have D n-bit random strings. So we just run our randomized algorithm A on X with random strings R1 through RD. These are n-bit strings. And we do the usual thing, right? I mean, if they all say yes, then we overall output yes. Otherwise, if one of them says no, we can output no. Okay, we say yes if all answers are yes. Okay, and let's do the analysis of this. Well, several things are very good. So this is a poly n time algorithm. In fact, well, it involves t as well. So let's just put that in a box since we're talking about here. The time for this algorithm is, well, poly n to compute these d different strings, plus we ran the algorithm d times, so poly n plus d times t. Okay, so compare that with the naive or standard repetition method. Okay, we added poly n time, but that's nothing too special. And of course, if the string x is in the language, then all of these runs, no matter what random coins you use, because we have one-sided error, all these runs will give you back the answer yes. So you'll overall answer yes, so that's fine. So the only thing we have to worry about is, suppose the string is x is not in the language, what is the probability that will incorrectly overall say yes? Okay, so let's think about this for a moment. If the string is not in the language, then our assumption here is that the probability over our random input for A, random coins for A, that you incorrectly say yes is at most 1%. Okay, and so, we're going to be feeding in for our random strings, vertices from this set R. These are named after n-bit strings. And what I want to do is think of the set B of, the set B of sort of bad strings for the algorithm A. I'll call it set B. And what I mean here is let B, let's do this in white. Let B, subset of R, be the, at most, 1% bad strings, random strings, for A on X. Okay, the ones that cause it to incorrectly say yes, even though X is not in the language. And now, in order to analyze, the probability, we'll use any of those, or we'll use all of those strings. Let's let S be a subset of L be the set of bad choices for little l. Okay, so remember this is little l here. And what does it mean for the initial choice little l to be bad? What it means is that the it means that the neighborhood of this vertex L is a subset of B. Right? Because when do things go really wrong? It's when you pick a vertex like this L, all of whose neighbors are in the bad set B. Okay, that seems quite rare, because then in that case, all your random strings R that you use will fall in the bad set B. Remember, those are the strings that cause A to incorrectly say yes, even though X is a no string. Great. Well, it seems there shouldn't be too many such strings, and indeed that's the case. So here's the claim. We claim that the cardinality of this set S is at most this magic bound 0.02 over D times 2 to the n. And why is that? Well, otherwise, if S is bigger than that, well, the first thing I'll do is let me just do something kind of simple. Let me just pare it down to a set of exactly that size. Choose any subset S prime of cardinality sort of exactly 0.02 over D times 2 to the n. Okay, maybe round that to an integer, but let's not worry about that. Okay, so just pare it down to some subset that has exactly 0.02 over D to the 2 to the n strings. And now the point is, like, this S prime is just small enough that we're allowed to apply the expansion hypothesis to it. So this S prime is an expanding set. And therefore, by the expansion property, the size of the neighborhood set of S prime is at least 0.8 times D times the size of S prime, okay, which is 0.8 times D times 0.02 over D times 2 to the n. And just the point here is that the d's cancel out, and this is 0.16 times 2 to the n. And that 0.16 is cooked up to be, well, greater than 1%. So actually greater than 1% times 2 to the n by quite a bit. Okay. But now let's think about this. Every vertex in S L has its neighborhood in B. And in particular, every vertex in S prime has its neighborhood in B. So we know that for all L and S prime, the neighborhood of L, that single vertex, is a subset of B. Okay, so that just means that the neighborhood of S prime is a subset of B. But we know that the cardinality of B is at most 1% times 2 to the n, right? Because what is B? It's just the set of bad strings for A. Okay, and by assumption, the set of bad strings for A is at most 1% of all strings. Okay, and now we have our contradiction because, well, of course, this on one hand, we saw that the neighborhood of S prime had size bigger than 1% times 2 to the n, but it's a subset of B, and B has size only 1% times 2 to the n. Okay, so that's a contradiction, and that proves our claim. Great. Okay, so now what do we finally conclude from this? Well, it's that this set S of bad initial choices little l is quite small. It's at most a 0.02 over D, fraction of all initial L. So the failure probability, or the wrongness probability of our algorithm, is bounded by 0.02 over D, the probability that the initial little l is in S. So what we finally conclude here is that for this new algorithm, the derandomized algorithm has error probability at most 0.02 over D. And this is great. So, I mean, if you, well, because in particular, it only uses n random bits. Okay, because the only random bits we needed were to choose this initial L. Okay, so let's compare it. What we have is, okay, we have polynomial in n, which is fine to assume, plus d times t time. So it's roughly the same as like the naive algorithm that just repeated d time. And we use only n random bits. So this is why I think it's like a magic trick. Like, we didn't use any more random bits than just a single run of the algorithm needs, which is kind of amazing. Compared with the naive algorithm, which uses d times n random bits. And okay, we don't get the error probability down to 1% to the power of d. We get it down to more like constant over d, rather than exponentially small in d. Okay, we get it down to 0.02 over d. Okay, so that's, if d is 64, then we got it down to 0.01 over 32. So we, took a factor of 32 off the error probability, while only increasing the running time by a factor of, 64. Okay, so in general, you get like linear error decay as a trade-off with the amount of time you use. But kind of amazingly, you use no more random bits. So that's kind of amazing. Let me end here by, this is kind of a somewhat simple way to use expander graphs to do derandomization. There's a bit of a more standard way that gives you, can give you this exponential error decay. So let me just put this as a remark. If you use a similar idea, but you take like a very large expander graph, not necessarily bipartite, but think of just a regular usual graph on, again, 2 to the n vertices. So you need fully explicit expander graphs. And so each vertex name is like an n-bit string. You can take like such a graph with, let's say, regularity 8. So every vertex has 8 neighbors. And then what you can do is you can generate a bunch of n-bit random strings by picking one initial random n-bit string, like we did, paying n bits, and then doing a random walk. And as you do each step of the random walk, you only have to choose a neighbor, so you only need to pay 3 bits of randomness, if the regularity is 8, to get to a new n-bit string, and then you get to a new n-bit string, and so forth. And you can show, actually, that this achieves sort of the exponential error decay. So let me write this. Using this idea of like a length t, random walk on a non-bipartite, let's say 8 regular. Just pick that because it's a nice power of 2 bigger than 3. 2 to the n vertex expander graph, which of course you need a fully regular expander graph to get that. You'll use, again, as you take this random walk, you collect up t n-bit random strings, and then you run your randomized algorithm A using each of them and say yes if and only if all of them say yes. You use n plus 3t random bits. Let me just write it as n plus order t random bits. Those pluses and t's look similar, so n plus order t random bits, n plus 3t random bits. And you can show that the error actually goes down exponentially. It's like at most 2 to the minus theta of t. Okay, so it doesn't go down just like 1% to the power of t, but it goes down like some constant to the power of t. And I won't prove this, although it's not too hard. The analysis is extremely similar to the analysis we did in the last lecture about how random walks in an expander graph, or a graph that has its minimum conductance large, or its second smallest Laplacian eigenvalue large, mix very quickly. So the analysis is very similar if you want to prove this fact. And not only that, this is about, the way I've described it is about reducing error in one-sided error algorithms. But this can also be proved for two-sided error algorithms. You can equally well take them, and at the cost of n plus order t random bits and t repetitions of the random algorithm, reduce even a two-sided error algorithm down to two-sided error that's exponentially small in t.